our invitation, and we indeed honored to have you. And as we said, this is a 5-day FDP on nonlinear dynamics in mechanical and physical system, and we had a series of lectures by some of the speakers who work in nonlinear dynamics. So with these words, I invite you to start your lecture, and uh, I hope I'm sure many enthusiastic participants who have been interacting with the speakers before, they will keenly looking for your lecture ahead. Thank you so much.
Thank you. Thank you, Ashok. Good morning, everyone, or to all the participants. I hope you enjoyed the workshop for the last 3 days, maybe. And I'm Jayaprakash. I'm from the discipline of mechanical engineering. So I have, let's say, the luxury of, in fact, having the whole day for myself. So what I will be doing is, I have segregated my talks into 3 main topics. So the first topic would be on stability and bifurcations. So over here, we will start with some very basic things. As I understand, most of you are aware of all these things, but there are some nitty-gritties that I might just point out so that we do have a better launch pad for going to what is called bifurcation theory and what is called center manifold reduction. And some of the typical bifurcations, some mechanical system examples where these bifurcations are observed, and what is the characteristics of mathematically, what are the characteristics of bifurcation, we will in fact talk about. When we talk about stability, the picture, or let's say the GI file on your screen, happens to be what is called the Jani-Bekoff effect, or intermediate axis theorem, or tennis racket theorem. We will see what it is. So this is a very interesting topic, because once again, the concept, the idea, the notion of stability comes into picture here also. Whatever we would in fact talk about in stability theory, we will in fact apply to this particular problem. It's a rigid body dynamics problem. So where there is a torque-free motion of a certain object, and you will be able to see what really happens. It is actually flipping. And why does it happen? What is the mechanism? Is it avoidable? Is it unavoidable? We will in fact talk about that. So later I will be talking about the second topic I have looked into, happens to be on nonlinear oscillations. So wherein I would be discussing some part of nonlinear normal modes, their excitations, their correlation to linear normal modes. In some of the mechanical systems, very specific mechanical systems. So because what happens is in nonlinear dynamics problems or nonlinear systems, the same methodology may not be applicable for every problem, actually. So what happens is when you classify the nonlinear systems, nonlinear mechanical systems in that particular sense, there are methods for applicable for each one of those systems. Okay, there is no general method which is always applicable. So that's the reason we will in fact talk about 2 very specific mechanical systems, and then talk about their normal modes and how do we in fact look at the normal modes, so on and so forth, making some definitions. Then we'll be talking about wave propagation theory. So more specifically, I will talk about something related to what is called the sine-Gordon equations. And when we talk about sine-Gordon equation, you do have a plethora of solutions that it can in fact show up, or it can exhibit in that particular sense. It can have soliton solutions, it can have breather solutions, and it can have a traveling breather, stationary breather. We will in fact touch upon only 1 or 2 of them in this particular lecture, part of lecture, because talking about everything mathematical analysis would take a lot of time. So I'll just give brief overview of all these ideas. So the last topic I have in fact set up is with regard to some aspect of granular systems, wave propagation in granular systems, which are usually the strongly nonlinear system or essentially nonlinear system. We will talk about what is strongly nonlinear or essentially nonlinear in a bit. So that would be the last part. I hope we will be able to reach up till that particular point, and we will see how how many things we can in fact touch upon. And once again, if you have any questions, I would request you to in fact unmute yourself and speak, because more often I may not be seeing at the raising hand button over here. So you can unmute yourself and speak up. So what I will be doing here is I will be making a presentation on the right side of my screen. And on the left side, I have my iPad where I would be writing something, maybe just scribbling something over here. So I will be using both these modes so that it is easy for me to in fact interact with you. Everything may not be on the slide. And just be aware that my slides would be quite dense. In a sense, I would be putting up too much information there. But obviously, if you do have the recording, you would be able to see that once again and recap a lot of things there. Okay, and you don't have to read everything on the slide itself. I would be trying explaining something a bit different than what I have written on the slides also. The slides would become more of a reference for you to in fact recap all those ideas and notions that we are talking about. Okay, so let's start with this talk on stability and bifurcation. So as I said, I'm Jayaprakash. I did my PhD from University of Illinois Urbana-Champaign and Masters from IIT Kharagpur. I basically work in the area of linear and nonlinear structural dynamics, vibrations, oscillations, wave propagation in nonlinear lattices, more often on order granular media, microfluidic droplet lattice, some aspect of acoustic metamaterials, chiral based networks. So, and we do have a small experimental group also, or experimental lab that we tend to do work on problems related to, let's say, bilinear stiffnesses, cracked beam problems. So this is my quick introduction. So to begin with, this might be the initial few slides might seem repetitive for someone who have attended my lectures or courses previously. But for the benefit of others who might be attending for the first time, I thought this would be interesting to start with, because I start with the statement, why? Just because whatever are the dynamical systems that we talk about in this particular course actually adhere to this particular statement by Laplace. Okay, so what it says, so we may regard the present state of the universe as the effect of its past and the cause of its future. An intellect which at a certain moment would know all the forces that set nature in motion. So when I say all the forces that set the nature in motion, it's in fact the equation of motion for us. Okay, when we talk about, let's say I talk about a simple pendulum. So what are the forces acting on it? I do try to balance it using Newton's method, or I use Euler-Lagrange equations or Hamiltonian formulation to write the evolution equations. That evolution equation encapsulates every information of that particular system. Now, is that just sufficient that I have an equation? No, it is not sufficient, because the solution of that equation would give you a general solution. Okay, but if in case I know the states of the system at a certain certain time instant, so what really happens is the future is known and the past is also known to me. Okay, so the future is predictable, the past is also predictable. So which necessarily means when I say past, I'm talking about time negative. I start at a certain time instant, I can go back in time and see what really happened to me previously. And I can go in the future also to just predict what happens. Okay, so that is in fact what the statement in fact says. Okay, obviously it is in fact applicable to classical physical systems or mechanical systems. It is not applicable to quantum mechanical systems. Quantum mechanical systems come into play when we talk about let's say the probabilistic ideas over there. Okay, so more often than not, let's say quantum mechanical systems are applicable even in the macroscopic levels also, but the probability that we are talking about is sufficiently small because of the Heisenberg uncertainty principle, that the the let's say the position and the momentum of a certain particle is not in fact exactly predictable. It is predictable within a certain probabilistic measure. Okay, within a certain probability range, it would be able to predict it. So in fact, we would end up getting what is called the Schrodinger equation for that probability. So even in this particular case, when we talk about sine-Gordon equation, we end up getting that same Schrodinger equation, but obviously the sine-Gordon equation that we would talk about is in fact deterministic. It is not probabilistic. So the statement is not applicable for probabilistic systems or stochastic systems. Okay, it is not applicable to time delay systems also, because in this particular case I'm just talking about one state, one point in my whole time evolution. If I know that, I will be able to know what is the future, what is the past. But as I remember when CP was in fact talking the other day on delay differential equation, you need a history. You can't just talk about one single point and say I know future and past. You need a certain history to determine its evolution further. Okay, so in that particular sense, it may not be applicable once again. But still, there are, as I said, in thermodynamical systems, because statistical mechanics, obviously, you will have the same issue. Okay, so you talk about probability density functions and you will not be able to predict it. Statistical averaging would be done, so on and so forth. But still, this statement makes a lot of sense. Why? Because most of the equations that we would in fact end up writing happens to in fact adhere to this particular idea, particular notion statement over here. Okay. Obviously, when I say equation of motion, you can just ask me, will I be able to write an equation of motion for a large water body or large ocean and incorporate all the forces acting on it? No, not really. Why? Just because we do not have the capability to write a governing equation for such large systems. And there are certain factors, certain forces which are not known to us as such, or we do not have a measure, or we do not have a functional form of those forces. So this equation of motion is not, not clearly written or completely written. But if you can write the equation of motion quite precisely, obviously this in fact satisfies. Okay. So in this particular sense, there are two key concepts that we are in fact seeing here. One is what is called the determinism. So what do I mean by determinism? If I know the certain state of that system, when I say state in mechanical systems, I'll talk about the generalized coordinate and the generalized velocity correspondingly. In a Hamiltonian system, I will call it as, let's say, the canonical variables of coordinate and its conjugate momenta. Right? So these are the states that I'm in fact talking about. So I will be able to know the future. So what is the basic idea, basic governing law that we are thinking about? It is in fact the determinism. Okay. So, or more often, it is usually called the conservation of information. So let's talk about a flipping a coin. I think people would have played this for fun. Okay. So let's say that whenever I do toss a coin, I do not know what would be the outcome of that particular experiment. Okay. The outcome would be probabilistic. But let's make it deterministic. Let's say that whenever I flip a coin, if I start with head showing up, then I would come back to head itself. Okay, so if you just talk to a small kid out there in the playground, they have a notion that if they start with a head, they would come back to head. If they start with a tail, it would come back to a tail. Okay, they have a certain notion. Okay, so it is usually somebody might have told them, but that's obviously not the case. It is probabilistic. The probability obviously would be 50%, which happens to be the case when you do infinitely many number of trials. Okay, but because we're talking about deterministic system, I would say that I do have a two-state system over here. Okay, so the head is one state and the tail is the another state. If I start with a head, I would come back to a head only. Okay, that's my dynamical law that I do have. Or let's say that's a kind of a gamed coin. Okay, let's say that I have gamed my coin such that so it is in fact always if I start with a head, I would come back to a head. If you end up getting such a coin, obviously you would be winning all the time. Maybe it is somewhat similar to, let's say, in the movie Sholay, He has a coin which has head on both sides. Whatever you do, you get a head. Okay. So let's say that that's a dynamical law. So you have to know, you have to be deterministic what would happen next. It can't be probabilistic. All our dynamical laws are in fact of that particular kind. Okay, it is non-linear, linear doesn't really matter, but it would in fact satisfy this particular rule. Similarly, another rule could be if I start with a tail, it comes back to a tail once again. As simple as that. Or let's say I can have a dynamical law where it is something like if I start with head, it goes to a tail. If I start at a tail, it goes back to a head corresponding. Okay. So wherever I start, it goes to the second state, not stay at the same position correspondingly. So now this is a two-state system of a simple coin. Let's talk about a rolling of a dice experiment. Okay, so a dice obviously has 6 faces and they are numbered in this particular form. Let's say that I do have a rule dynamical law of this particular kind. I start with a start with 1, I go to a 2. If I start with 2, I go to a 3, so on and so forth. Now, once again, this is a deterministic system, which means wherever I start, I know where I would be going, and I also know where I have come from also. Right? If I stand at 6, I know if I just roll it once again, I will be going to 1. And similarly, if I start at 6, I know where I came from also, because I just need to take a step backwards in time and I would be able to see I was at 5. Okay, so that makes it once again a deterministic one. Now I have just jumbled up a bit over here in this particular case, but still if you just put it together, you would be able to see that this is a deterministic system once again. Okay, the law is in fact deterministic. That's the basic premise, that's the basic idea that we are in fact talking about. So does our simple pendulum, let's say I do have a simple pendulum equation, because we will come back to this particular equation again and again. I have normalized everything. So theta double dot plus sine theta equal to 0 is a certain dynamical system. Okay, so it's a nonlinear system that we have got here. So does this in fact satisfy this deterministic condition? Yes, it's perfectly a deterministic system. Okay, so let's say that I start with a certain initial condition theta 0, theta dot of 0 is, let's say, theta 0 dot, or let me just put this as V0. Okay, so just for the sake of simplicity, I start with certain initial condition. I would be able to know what is its future and what is its past. Okay, that you can easily verify. Okay, and once again, some of you might be thinking about how did we in fact get to that particular idea that there exists a solution and it is unique also. Okay, there is a formal proof of what is existence and what is uniqueness of solutions also. So you would be able to easily verify that the vector field that we are in fact getting, I think CP was talking on the other day of writing it in the state space form. I would just write it as theta dot equal to phi dot equal to minus sine theta. So if I just put it this way, theta dot phi dot is equal to phi minus sine theta. Okay, so this is my expression on the right hand side. Okay, so let me just call this as f1 of theta comma phi, f2 of theta comma phi once again. Sorry, so let me put it here. Okay, so I would call this f1 and f2 happens to be what is called my vector field. Okay, so you know what is a vector field. I think we'll come to that particular point also. So when I talk about my state space over here, so I'm just trying to make it precise in this particular case. This is my state space theta and phi. Any point here would in fact be an initial condition for me, because it would just tell me what is the position and velocity. And this position and velocity would in fact give me a direction for its traverse. Okay, any point for that matter. If I start anywhere here, it would tell me where I would be going forward at that particular time instant. Okay, that's the reason it is called a vector field correspondingly. Okay, because obviously theta dot would tell me in the theta direction what would be my magnitude, okay, in that particular direction for evolution further. Okay, similarly for phi dot also correspondingly. So that's the idea of a vector field, and obviously the pendulum in fact satisfies this determinism condition. There is another notion, obviously from that particular statement, what is called the reversibility. So what do I mean by reversible? Obviously, I'm talking about a solution. So whenever I write a solution, theta of t, okay, I never restrict my time to be positive. Okay, I do not have to restrict my time to be positive. Why should it be restrictive? Right? So whenever I talk about a dynamical system, I should be able to go back in time also. Let's say t plus 10 is what I would want to see, or let's say t0 plus 10. So t0 happens to be 0 for me in this particular case. Similarly, I should be able to find out what is t0 minus 10 also. So t0 happens to be my initial time instant at which I have provided my initial condition. So I should be able to go forward and backward in time. So that's the concept when we talk about this going back in time. I do have what is called the reversibility. Our dynamical law should in fact be reversible also. Let's consider a simple dynamical rule over here for a three-state system over here. Okay, I have as let's say someone has created a three-faced dice. Okay, so I do start with 1, I go to 2. So I and at 2, I would go to 3. And from 3, I go to 2. In forward direction, I know where I'm going. No issues with that. This is deterministic. Okay. But is it reversible? So what do I need to do for checking the reversibility of my dynamical system? I just need to flip my arrows over here, and then I do have a problem. Okay, what is the real problem here? I start at 1, I do not know where I should be going. Okay, I get stuck at that particular state. So let's say that, I mean, just to motivate you to think about it. So let's say that I would have a van der Pol oscillator. We will come to this also later. Let's say that I do have a van der Pol oscillator, and this is once again my state space x dot, and this is my limit cycle oscillation. Okay. So now I start somewhere here. What really happens is my equilibrium point in this particular case happens to be unstable, right? So the equilibrium point, there is only one equilibrium point in that particular case that happens to be unstable. What happens is it would go to this particular limit cycle. Now, if it ever reaches the limit cycle, obviously I would lose the determinism, because once you reach that limit cycle in finite time, in space finite time, let's be precise, in finite time, then I would lose the determinism just because I will never be able to go back in time and check where I came from. Okay, because if it goes to a limit cycle oscillation, I would lose all information for myself. Okay, somewhere similarly, if I go back to my equilibrium position here, let's say this is my equilibrium position. If I ever will be able to go back to my equilibrium position in finite time, then also I would lose my information. Why? Because I will never be able to know where I came from. Because if you start at your initial position at the equilibrium position itself, you will never know, you will never be able to evolve. Right? If you start at the equilibrium position, you will never be able to evolve. That's the basic definition of an equilibrium point also. Okay. So in that sense, you will never be able to reach a limit cycle in finite time, or you will never be able to go to an equilibrium position from any other state. Okay. So if you do that, obviously you would lose this reversibility and determinism. That's against the law of classical physics that we in fact spoke about. There is loss of information. Information conservation doesn't happen. There is loss of information, so that cannot happen. Okay. Now, where is the reversibility failing here? In this particular case, if I start at point 2, I know I have two states I can reach, 1 and 3. Okay. But if I start at 3, I know where I will be going. Okay. And I also know where I came from. But at certain states, I will never be able to know where to go further. Okay. So there is loss of reversibility in this particular sense. Okay. So our dynamical law should in fact be both deterministic and reversible. Right. That's the reason if you have taken a very formal course on nonlinear oscillations, we would always start with the premise of saying that we do have an existence of a solution, okay, and the uniqueness of a solution. All right. So obviously you would have spoken about Lifshitz continuity, or let's say the differentiability, or let's say the continuity of your vector field correspondingly. Lifshitz continuity, it is in fact a bit more relaxed form of general differentiability of your vector field in that particular sense. Lifshitz continuity is in fact taken in a bit different context, and it's a bit more relaxed condition that you can in fact impose. Okay. So this is reversibility as such. So both the deterministic and reversible. And there are certain conservation laws we would in fact talk about. We will come to this also in a general vector field. Very quickly we will go through this. So if your system in fact reaches only very few states, let's say that I do have a dice that I have got here, which with 6 numbered faces. And whenever I start with 1, it can reach only 2 and 6. Or let's say if I start with 2, each of these is in fact deterministic and reversible also. There is no loss of reversibility or determinism. But if I start at 1, I can never reach 4. And 1, 2, 6, if I start with any one of them, I can't reach 3, 4, and 5. Okay, which means there are certain states that the dice can in fact reach when you start with either of these things. Okay, so it forms one loop over here that would end up getting a certain measure, what is called the conservation law. In that particular sense, there would be a certain measure for that we would talk about later. So you would be able to reach only very few states, and that's what is called the conservation, right? There is certain quantity that would be in fact be conserved in that particular sense. So you will never be able to reach every state of your dynamical system for that matter. Okay, so when I talk about conservation, I think in a mechanical system, I would have conservation of energy. That is one quantity, that's a scalar quantity. Similarly, I would have conservation of momentum, okay, translational or let's say linear momentum, and there would be conservation of angular momentum also. There are a total of about 7 of such conservations that we can in fact talk about. But obviously, there can be several more conservation laws by combination of other quantities that we can in fact think about, which may not have very specific basis on the idea of energy or let's say the momentum itself. But when we talk about conservation laws, you can in fact think about this particular idea that the system would reach very limited number of states in your particular phase space or state space. Just be sure that when I talk about state space and phase space, you just need to be a bit, they are not same to be precise. Let's say I have state space. I'm talking about something like, let's say, qi dot. Okay, so a generalized coordinate and its corresponding velocity. When I talk about phase space, I talk about qi and pi. Okay, so this is generalized coordinate. This would be generalized velocity. So this is generalized coordinate, and this is conjugate momentum, or let's say, let me just momentum. So when we talk about, let's say, Lagrangian dynamic, state space is sufficient for us. We don't have to bother about what is called the phase space. The idea of phase space, or let's say the notion of phase space, comes into picture when we talk about what is called Hamiltonian formulation, or let's say Hamilton-Jacobi equations or Hamiltonian systems, symplectic theory, so on and so forth. I don't think we are in fact interested in going there. In case I just use phase space or state space, as of now for this particular set of lectures, you can just imagine that I'm talking about coordinate and its velocity. Okay, sometimes we interchange that. More from a classical perspective, we shouldn't be doing that, but sometimes it happens. So you can just imagine that I'm talking about state space itself for that particular matter. Okay. Now, coming to the dynamical systems itself, there are different sources of nonlinearity. Obviously, there is no system which is completely linear. So linearization is in fact an idealization, the luxury that we have got for certain set of systems. So where can these nonlinearities come into play or come into picture? It can be in the form of nonlinear stress strain relations. Obviously, whenever you do so tensile testing, obviously you would get a certain region which is in fact linear in the initial stage. Then it becomes nonlinear, obviously, right? And most of the systems that we in fact talk about or we in fact look into would be in fact evolving within this particular region where it is in fact linear. But not obviously the case that so every time it has to be here, or it can be the nonlinear stress strain relations can come into picture because of, let's say, nonlinear elastic materials. There can be polymeric materials which show nonlinearities. So stick slip, piecewise linear springs, all these are in fact nonlinear in nature. And there are geometric nonlinearities which are because of the large deformation. This is a very simple case that you are in fact seeing here. Once again, the post-buckling analysis that I think CP was talking about the other day happens to be in fact a geometric nonlinear problem in that particular sense, because you do have large deformation over there. Till the point it buckles, obviously we will talk about linear and I'll show the bifurcation that we are in fact talking about in a later lecture. That obviously leads to large deformation, which is in fact happening here. And obviously boundary conditions. So the boundary condition, free surfaces and fluids leads to nonlinear boundary conditions or deformation dependent constraints. Let's say I do have a beam and it is not your regular cantilever beam, but I do have a certain region over which is in fact conforming to as it deforms. So my boundary condition is in fact changing as it deforms, right? So at a certain point here, the beam would in fact look something like this, right? So over here, the other region would have just in fact resting on my region here. Let's say I'm just writing it bit crudely over here. So it would be tangential to that particular point in that sense. Okay. So those boundary conditions obviously would be deformation dependent and leading to nonlinearities. And what others? Bilinear springs. Obviously, if you have a stop, so what happens is at this particular point, there is a change in stiffness. Okay. After a certain deformation, after delta x goes beyond delta, I do have k1 plus k2. Before that, it is k1. You can in fact say that this is linear. Okay, so this is linear in two pieces. So two pieces of linear systems are juxtaposed together, and at that particular point I would be able to match my conditions. But still it is a nonlinear system, essentially nonlinear system. Why? Just because you do not have a linear structure in this particular problem. Two independently, you would be able to say they are linear, but when you put them together, it's a piecewise linear system. So it is essentially nonlinear in that particular sense. So what others? I think this Huygens pendulum, I'll in fact show a very interesting simulation also. Why is it so interesting? We will see that. Once again, electrodynamic forces, electromagnetic forces in this particular sense, most of them happen to be in fact nonlinear in nature, obviously all the analysis that we end up doing happens to be linearized dynamics. Okay, so when we talk about essentially nonlinear systems, there are very few that we can in fact think about. We will see how it works there. Okay, so let me just show this particular animation over here. I have three different set of pendulums. Okay, so the first pendulum over here, I start with a certain initial condition, which is pi by 4. Okay, so, and I'm showing the time series for both the nonlinear pendulum and the linearized version also. When I say linearized version, I may have to linearize it about an equilibrium position. The equilibrium position is 0. Okay, that's where you would have oscillatory solutions. So what you end up seeing for an angle which is equal to pi by 4, the time period difference is in fact sufficiently small. I think this is pi by 4. Yeah, that's pi by 4. Yeah. So you would see that the time series are extremely close, right? If you go much smaller, I mean, the angle, initial angle is much smaller, obviously it would in fact be much better also. That's the reason the linearization does work for us, just because the linearized system and the nonlinear system do exhibit similar characteristics. Okay. Now, in the second simulation, I have considered this to be pi by 2. Okay. And what you end up seeing is the nonlinear system, the linear system do have a large deviation. Okay. So the time series shows a large deviation. Just note that the amplitudes are same. The amplitudes don't change in either of those cases. Okay, why? Just because we are talking about a conservative system. There is no loss of energy in this particular, in either of these cases. Okay, so there is no change in amplitude, but if you just see this over here, the time periods are different. And the frequency is constant. Frequency is not changing with time. The frequency would in fact be a constant value, but obviously after each cycle there is a certain addition of delta t, and it just keeps on becoming larger and larger. Okay, so because at each cycle there is an addition. Now let's go to the other limit sufficiently close to pi. Okay, so this is pi is 3.14. I considered it sufficiently close as my initial condition. You would see once again the linear pendulum, obviously it doesn't care about what is your initial condition. So the linearization, the equation would come out and you'd be able to just start with any arbitrary initial condition. It will not restrict you. Okay, it will not tell you your initial condition is very large, so I won't be able to integrate. No, it doesn't tell you anything. It's the user thought that needs to go there, that if I just make it sufficiently large, my linearized model is no longer valid. Okay, that's the discretion of the user, not of the model. Model doesn't tell you anything. Any initial condition, it would just integrate. Okay, it would just give out a solution corresponding. So when you go to that particular limit, what you see is the time period is much, much larger. Okay, so what is that you are in fact seeing here from pi by 4 to pi by 2 to sufficiently close to pi, you would see that the time period is increasing, which means the frequency is decreasing. Okay, so what we have in a simple pendulum and a simple nonlinear pendulum is a softening nonlinearity. Okay, a softening nonlinearity, which in fact means as you increase the amplitude, the frequency decreases or the time period increases correspondingly. But in the case of a simple pendulum, the linearized version, it's an isochronous oscillations. What do I mean by isochronous oscillations? The frequency is independent of the amplitude of oscillation. The frequency would remain the same. No matter what initial condition you start with, the frequency would remain the same. That's the beauty of a linear system. Maybe that's a drawback of the linear system also in some sense. Okay, so those are what are called isochronous oscillations. So now one can ask, is the amplitude dependence, or let's say frequency dependent amplitude, is it a characteristic of a nonlinear system? Not really. In fact, you can't make a statement of that particular kind. Why? Just because of the next example that I'm showing over here, which is in fact what is called a Huygens pendulum. So as I said, it's in fact having a nonlinearity where the boundaries are in fact being the cycloids. Okay, you know what is a cycloid. I'll not go through the definition of what is a cycloid and derive the equations over here. So it's these two are cycloids, and on both sides, the string in fact wraps around this particular cycloid over here, and I start with three different initial conditions. So once again, this is pi by 4, pi by 2, and maybe 3 pi by 4 or something. I don't know the number here. Okay, I start with three initial conditions correspondingly, but very, very interestingly, this is a nonlinear system, mind you. So this is the equation. Please go back and just look at what is the Huygens pendulum. You can easily derive it. Okay, so there is no much issue in deriving this equation. So I didn't spend any time in fact doing that. So what really happens here is very interesting that come what may, whatever might be the amplitude, you would end up getting the same time period, or let's say the frequency becomes amplitude independent. It's a nonlinear system, but shows isochronous oscillations. Okay, so the frequency depending on amplitude may not be a characteristic of a nonlinear system. Right? There are several systems, several mechanical systems which can be made isochronous. I think some of the papers you can look into by Richard Rand. He tries to work out ways in which you can remove this amplitude dependence. By adding certain nonlinearities, you are trying to remove the amplitude dependence. Okay, so that can be in fact done. So don't ever think that every nonlinear system would have a frequency which is amplitude dependent. You can't generalize that as a statement. But most nonlinear systems that we talk about do show this. But if you can find out that particular relation, well and good. If you can't, I think this is a very classical example of a nonlinear system with isochronous oscillations. Okay. So now, as I said, we need to understand different kinds of nonlinearities, or let's say different classifications of nonlinearity, because most of the methodologies that we talk about in this particular lecture or maybe in your courses happens to be relevant to very specific class of nonlinear systems. So there are something called weakly nonlinear systems. So let's say that this is a linear structure, x double dot plus x. Obviously, I don't have to spend time on telling that x is a displacement, so on and so forth. I presume that you already know this. And I add a certain nonlinear term over here where n happens to be the index, which is in fact greater than 1. Okay, I'm just using it as a simplification that n is greater than 1, usually integers. It can be fractions also, I'll show a bit later. Now, epsilon is a small parameter that I'm adding here, which is sufficiently smaller than 1. So what really happens for small values of x, obviously this nonlinear term is in fact sufficiently weak when you compare to the inertia term, or let's say the linear restoring force term. So such kind of system, if you can classify them or if you can model such a system as in this particular form, you will call this as a weakly nonlinear system. Okay. Now, if there is no epsilon, or rather, I would say that x is sufficiently large and x power n is of the same magnitude, or let's say similar magnitude as x itself. When can that happen? When x becomes sufficiently close to unity, they are of the same magnitude. Okay, let's say x is 0.8 and n is in fact here 3 or 2, let's say. They can be of the same order of magnitude. So I may not be able to neglect it. So what I talk about is a strongly nonlinear system. The nonlinearity is stronger. Okay, then I will never be able to say that a weakly nonlinear, I will never be able to say there is a linear structure. I will add the nonlinear terms and use the asymptotic methods or perturbation method. There is a limitation here. So these are what is called strongly nonlinear system. The last classification that I can make here is what is called a truly nonlinear system or essentially nonlinear system. If you just look at it here, there is no linear structure. Okay, if you try applying your asymptotic method or perturbation method, it never works here. Okay, so the asymptotic method has a basis, or let's say has its roots in the idea that there is a linear structure, and Over and above that linear structure, the nonlinearities would add corrections. But the linear structure has to give you the solution that you are looking for. Okay, so the linear structure, if at all, I will just give you a very simple example here. Let's say that I do have a system of this particular kind, x cube equal to 0. Okay, so x double dot plus x cube equal to 0. I can easily prove that this has oscillatory solutions. Okay, so this has periodic solutions for sure. How you will do that, we'll come back to that particular part later. But let's say that I will use perturbation method straight away, x0 plus epsilon x1 plus so on and so forth. So I will just have this particular case here. So I will just change this to x double dot plus epsilon square x cube equal to 0. I have just scaled it this way, epsilon x. Okay, x I have just replaced it with epsilon x and just have removed everything. Now if I just put it back into my equation, my order 1 equation happens to be x0 double dot equal to 0, which would give me a solution which is x0 is c1t plus c2. Okay, I'm assuming that you already know what is asymptotic method. We'll talk about it very briefly a bit later. So you would end up getting a solution of this kind. But as I said, very clearly, I know that this has periodic solutions. We can easily prove that. Why? Just because if you just write its potential energy, so I'll just give it out here. So this is x, v of x. So what would be its potential over here? This would in fact look something like this. So this would be x power 4 divided by 4. Okay, because your restoring force happens to be minus del v del x, right? Because it's a 1 degree of freedom system and I do have a 2-dimensional state space as well. So what I do end up getting is x power 4 by 4, which happens to have a certain flat bottom. Okay, so it has a certain flat bottom also. I couldn't write it that way, but you can easily see that this has oscillatory solutions. But your asymptotics is telling, if you blindly use your asymptotic method, it would tell you that it has no oscillatory solution. So the basic idea is whenever you talk about asymptotic method, it needs to have a linear structure which gives you the solution that you are in fact interested in. Okay, so x1 c1t plus c2, it happens to be uniform motion that we are talking about. All right, so the acceleration is in fact equal to 0. It has uniform velocity starting with certain initial displacement. So you need to be careful about when you can use asymptotic methods. Strongly nonlinear systems, you need to be aware till what region this asymptotic method is valid. Weakly nonlinear system, you can blindly use it, no big issue, because you do have a parameter which is sufficiently small, which you have recognized in your system. Essentially nonlinear system, asymptotic methods don't work. Okay, what works? I think that's a very simple idea. A harmonic balance method does work in that particular case, but obviously it has its own limitations. Let's not worry about that right now. For an essentially nonlinear system, a simple harmonic balance would in fact work. Why? Just because harmonic balance doesn't depend on linear structure. It starts with the idea of Fourier series expansion of any function correspondingly. I think I remember CP was talking about Fourier series expansion and finding the coefficients. You just impose a certain Fourier series expansion here and try balancing the harmonics on either side of your equation. You end up getting the corresponding coefficients. Okay, so harmonic balance method works here. A strongly nonlinear system or weakly nonlinear system, asymptotic methods need to be judiciously used, not with complete disregard for their validity. Obviously, in the case of a simple pendulum, I have just said, let's say that 1/6 is sufficiently small. This epsilon, I just replace it with 1/6 with an epsilon, because at a later stage, I can say epsilon is 1/6 for me. Because when we do the analysis, we don't a priori mention what is epsilon. Okay, nowhere you would be able to say what is epsilon. Is it small or large? It's a relative term for that particular matter. So I don't have to worry about it at this particular stage. Okay, I do the complete analysis, keeping it more like a bookkeeping parameter, then I can in fact use it. Or 1 by 6 can be considered to be some coefficient, multiply that with an epsilon. People tend to do it in a very different forms. I don't think there is any much issue over there. Okay. Now, once again, in the case of simple pendulum, obviously the same expansion works because I'm expanding it about theta equal to 0. But if I have theta sufficiently large, very similar to what really happened over here. Okay. So if theta becomes sufficiently large, you would start deviating, right? It might give you a solution, obviously, but it might be quite erroneous. So in this particular case, we will talk about, maybe towards the end of this today's talks, we'll talk about a problem related to granular systems, where there are two spherical particles which are interacting. As I said, n need not always be an integer. It can have a very peculiar power, which is 3 by 2 over here. And did I just generate it from thin air? No, it has its basics, or let's say it has its basis in what is called the Hertzian interaction of two convex surfaces. Okay, there are certain assumptions that we may have to make. We'll talk about it later. So if you talk about these two particles and they are sufficiently compressed, so delta happens to be the pre-compression that I'm in fact applying, I can in fact do a Taylor series expansion of this, and I'll see there is a linear term, or let's say linear structure. Okay, obviously I would be able to say in that particular case I do have a weakly nonlinear system, which whenever delta is sufficiently large, or let's say the pre-compression is sufficiently large, I can say it's weakly nonlinear. And once again, when x1 and x2 become sufficiently large, comparable to the pre-compression itself, I do have a strongly nonlinear system. And once again, whenever I do remove that pre-compression, that means there is no pre-compression that I can in fact have over here. What I end up getting is in fact a essentially nonlinear system. Right? When I say essentially nonlinear system, you can't do a Taylor series expansion here. You will never be able to do that in this particular case. Okay, so that's the reason I will say that this is a essentially nonlinear system in this particular sense. And I do have a subscript plus that I'm using over here. Just be aware of this, just because if the argument becomes negative, this term will give you an imaginary value. But x1 and x2 are real terms for me, or let's say they're real variables. They are not complex variables. So what really happens is whenever x2, the argument becomes negative, I may have to disregard it. What does it physically mean? Whenever it becomes negative, it loses contact with the wall. Okay, let me just show what is really happening over here. So this is, let me just write it over here. So these are two particles which are interacting with the wall. Okay. So let's say this is x1, this is x2. So this is the interaction that I'm talking about, x2 power 3 by 2 with a half. Okay. Whenever x2 is positive, I do have a restoring force, or let's say the elastic force acting on that particular particle. But whenever x2 becomes negative, obviously it loses contact with the wall. So there is a loss of interaction force at that particular location. So it becomes in fact equal to 0. Okay. So this would be the basic classification that you can in fact think about. Obviously, there can several other ideas that you can classify the nonlinear systems into, but basically this would be the framework. And most of the methods that we talk about today happens to be applicable to weakly nonlinear systems. Multi-time scales, obviously, it's a more general theory, more general idea, because when we talk about discrete systems, we talk about multiple time scales. But when we talk about wave propagation theory, even spatial scales can be in fact spoken about. We will in fact use that later when we talk about Sine-Gordon equation later. Okay. Now, coming back to the dynamical systems, obviously, you already know I can write it in the form of a vector field. Okay, I'm not using the curly brackets here, just maybe because of a sloppiness, or let's say I'm already writing it as x belongs to Rn. So where R happens to be the real space, okay, N happens to be the dimensions of the dynamical system, or let's say the state space that we are in fact talking about. Okay, so X happens to be a vector of N different values that I can in fact think about, and F happens to be once again a vector, okay, F1 to Fn correspondingly. So the rule that I'm in fact looking into, it takes Rn values, that is x1 to xn, and it would give me a number in the n-dimensional space once again. Okay, so F happens to be the total function, total vector field that I'm in fact looking into. So whenever it is not explicitly dependent on time, I call this as in fact a autonomous dynamical system, right? So whenever I do have a explicit time dependence, I do call this as a non-autonomous dynamical system. A very simple transformation of a non-autonomous dynamical system to a autonomous dynamical system can be in fact performed. Okay, where time happens to be the variable that I have got, I will define it as yn plus 1 dot equal to 1. When I just do a simple integration, that becomes yn plus 1 equal to t. So I would be able to convert my non-autonomous dynamical system to a autonomous dynamical system. A very simple trick. Why do I need it at the end of it? I don't think that it would be all that necessary in most of the cases. But in very specific cases, I think it would be better to use this particular formulation when we talk about, let's say, when we think about something like Poincare maps, I would have to take, whenever I look into non-autonomous dynamical systems, I would have to take time snapshots of my system at different time instants, where time would be the parameter. I would be using it in this particular context, or else it is not of great significance as such, but it is easily doable. That's something that you need to know. Okay, as I said, it's a simple vector field. What do I mean by, as I said, a vector field? Let's say if it is a two-dimensional state space that I'm in fact talking about, any point, if I just pick any point over here, it would tell me in what direction I would be evolving. Okay, once again, as I said, deterministic. So there are arrows that are in fact shown here. This is what is called a Cure plot. Okay, any point here in my state space would tell me what is the direction of evolution. Okay, that's the reason you would be able to evolve. So the dynamical system or dynamical law that I evolves it is f of x. Okay, so f of x would tell me in what direction I would be going further. Okay, so this is something that is already known to us. Okay, so let's make things a bit more abstract because we will go to some other aspects later. So let's say that I do have a non-autonomous dynamical system with a certain initial condition. Because obviously, when we talk about these state space, it is not finite space. Okay, it's an infinite space, right? And how many states are there? Infinitely many states would be there because it's a real space that we are in fact talking about. Of those real of that real space, I'm interested in very specific set of initial conditions or a subset of that particular higher dimensional space, which I would want to see how it evolves. Okay, let me just consider a three-dimensional state space. Okay, why just three-dimensional? Because physically, I will be able to write only 3 dimensions. Visualization would be easy. So let's say that this is a three-dimensional state space. I would be interested in looking at what happens to all the initial condition within this particular space, let's say. Okay, so this would be X belonging to some region D, let's say. Okay, so I would want to see how it evolves in time. Let's say after certain time duration, it would evolve to become something like this. And after certain other time duration, it might become much smaller, so on and so forth. I would just want to see how it evolves in state space. Okay, right? So that's in fact the basic idea. I do not have to pick up point by point, but I would want to take a bunch of these initial conditions. So that's the reason I talk about it as a small region over which I would want to evolve my particular system. So this is the basic idea. Okay. So what is really happening in this particular state space over here? So in the state space, I do have only the states, that is xi, xj, xk, n of them correspondingly. Time happens to be just a real number for me. It is not entering into my, let's say, even if it is a autonomous dynamical system or non-autonomous, it happens to be a real line that I'm in fact thinking about. Okay. At every time instant, I can just define a certain state, certain position here, from which I can evolve forward or backward correspondingly, right? Once again, I will just go back mapping from time space here to the state space, or let's say phase space is what I have written. It should be more often called the state space, as I said. Okay. So you will be evolving, or let's say mapping this time from here to here, T0, T1, T2, T3, so on and so forth. Similarly, T minus 1, T minus 2, so on and so forth correspondingly. So that's the evolution that we are in fact interested in. Now, obviously, as I said, I'm not interested in every initial condition, but subsets of U that remain invariant under the action of the flow. So f of x, or let's say the dynamical law, is what is called a flow, right? It is something like, as I'm showing here, it flows in the state space like a fluid. So that's the reason we call it as a flow. I think for a discrete time dynamical system, we call it as a map. If you are aware of that, I think that's what is called usually a map, okay, where it is not infinite states, but we are looking at the system at finite number of time intervals. Okay, so I don't see, because in this case I'm talking about time as a real value. But in the case of a map, or let's say a discrete time dynamical system, there is an index that I provide to my each state, and that would in fact be an integer for me. Okay, it could be positive or negative, doesn't really matter, but it would be an integer. So you're looking at only finite number of states in that particular sense. But here we call it as a flow because time happens to be a real value for us, a real number for us. Okay. Of all these regions, I'm looking at a subset which are invariant. What do I mean by invariant? Invariant in a sense, let's say that I do consider something called an equilibrium point. Uh, in that particular case, I know what is an equilibrium point, right? I believe you are aware of that. So the point in state space which doesn't evolve in time. Okay, if you start at that as an initial condition, it would never evolve from that particular position. Okay, so those are what are called equilibrium points or fixed points or stationary points. Then what is the second kind of invariants that I'm in fact looking into? What are called periodic solutions. Okay, so what is a periodic solution? If you start at a certain time instant, it would come back to the same position after a finite time duration. Okay, x of t, whenever I say x of t, it happens to have all the n variables, n tuples to be more precise. Okay, all these n of these values should in fact come back to the same position. So let me just put it this way: x1 of t, x2 of t, so on and so forth, xn of t is equal to x1 of t plus capital T, x2 of t plus capital T, xn of t plus capital T. Okay, so this is what is called a periodic solutions. Okay, once again we'll talk about equilibrium points, periodic solutions, so on. There is some other kind of solutions or invariants which is called integral manifolds. Just remember when we spoke about the rolling of a dice, and we said that there are certain conserved quantities, and the states would in fact reach only these many states. Okay, those can be considered as these integral manifolds correspondingly. Okay, so because if you stay on that particular manifold, when I say a manifold, you can think of it as a surface or a higher dimensional surface, or a curve if you're in a lower dimensional space, it's in fact just a surface for that particular matter. So because g of x, when I say x, x happens to be n-dimensional, so it would in fact be a very, very big, huge surface in a higher dimensional, n-dimensional space for that particular matter. Okay, so those are integral manifolds. There are what are called eigenspaces in linear dynamical systems. We'll talk about that particular part also. Okay, so these are certain invariant manifolds that we would be in fact talking about. What do I mean by invariant manifolds? If you stay on that particular manifold, you would stay there forever. Okay, you will never, in fact, if you can find that particular manifold, you start on them, you would just be on them forever. Okay, you would just be staying on that particular case. So first one of them, let me just put it this way. So first one of them, let's say the equilibrium point, it's a single point in state space. If you start there, you would stay there correspondingly. So let me just take a simple case here. Let's say this is x and this is x dot. Okay, so if you say 0 is my equilibrium position, if you start at 0, you would stay there forever. Okay, now let's say that I do have a periodic oscillation here, periodic solution, something like this. I start somewhere here, I just keep on moving and I come back to the same position after certain time duration. You would stay there forever. Okay, now, what do I mean by an integral manifold over here? Because let's say that I do have a conserved quantity in this particular case. Let's say that I did have x double dot plus x equal to 0. So x comma x dot equal to 0 comma 0 is an equilibrium point. Okay, as simple as that. And x of t is, let me just write it as a sine of t. Okay, so plus some phi, a comma phi are constants. Okay, amplitude and the phase correspondingly, that's a periodic solution. What is an integral manifold in this particular case? It would in fact be half x dot square plus x square by 2 equal to some quantity h. That's an integral manifold. Okay, so that's a conserved quantity for me in a sense that I do have the energy which is in fact being conserved. Okay, obviously, whenever we talk about integral manifolds, you need to have a conserved quantity there, and this is a two-dimensional space that I'm in fact talking about. Okay, if you start in this particular integral manifold, you will stay there forever. So similarly, if I say if I just talk about x, if I just insert it back here into my integral manifold, I'll find a relation between amplitude and phi and the energy level. Okay, for each energy level, my integral manifold would keep on changing. Okay, so this might correspond to, let's use a different color. This might correspond to, let's say, h star, or let me say h0. And this is another integral manifold. This would correspond to h1. Similarly, each of them would have a different integral manifold that I can in fact think about. Okay, corresponding to that, I will be able to say there is a periodic solution. So the dimensionality in each of these cases keeps on increasing if you just see this here. Okay, so it's a point in state space. Periodic solution would be a curve in state space. An integral manifold would be higher dimensional space in the whole state space. Obviously, the integral manifold should be of a dimension which is lower than the Rn correspondingly. Right? So it's in fact embedded inside that n-dimensional state space. It's a surface, a hypersurface to be more precise. Okay, because we are talking about a very general n-dimensional space in this particular sense. What is an eigenspace? I think we will come to that. Let me just not spend time on that particular point. Okay, so equilibrium point would be the starting point in any of your dynamical systems or nonlinear systems that we talk about. So what do they in fact necessarily mean? they in fact correspond to constant solutions which never evolve in time, or rather physical equilibrium of the dynamical systems, where the forces are completely balanced. Okay, the static forces are in fact balanced in that particular case, and you do not evolve from that particular position, come what may. Okay, unless you perturb it. Okay, don't tell me that I would perturb it and would it still stay there? No, it will not. Okay, that's exactly where we will talk about the stability of the equilibrium points. Okay, so if you just equate your vector field to 0, that would tell you that you do not want to evolve anywhere, right? As I said, if you just go back to this particular picture and say my vector field, it is showing me a direction and a certain magnitude also, right? It is not just the direction, it is also telling me what is the magnitude. If you say the rate of my increase or decrease or evolution rate, if I just make it equal to 0, obviously it would have to stay there. It can't evolve in any direction. Okay, it has to be made equal to 0 in every one of the f1s over here. F1 equal to 0, F2 equal to 0, Fn equal to 0 in total. Not that F1 to Fn minus 1 is 0 and Fn can in fact evolve. No, that cannot happen. Okay, in that particular sense. So this is a simple vector field making equal to 0, you would get an equilibrium position. Okay, now so these equilibrium positions are in fact the in state space. In mechanical systems, what really happens is the equilibrium position would always be on the horizontal axis, or rather it will not have any velocity, so it would be on the axis of the configuration space. Okay, let me just clarify what is a configuration space, because your mechanical system is what we are talking about here. Let's say that I do have a 2 degree of freedom system. So because we are talking about state space, let me just clarify what is configuration space in this case, because we will talk about this 2 degree of freedom nonlinear system a bit later. So what is config space here? Configuration space is 2-dimensional, which is x1, x2. What is state space? x1, x1 dot, x2, x2 dot. The representations can be a bit different in the cases. I think CP was using bit different notation. It doesn't really matter. So x1, x2 are generalized coordinate. When you combine their generalized velocities with them, we call it as state space correspondingly. So similarly, what is phase space? It would be x1, p1, x2, p2. Coordinate and its conjugate momentum. Okay, doesn't have any problem as such. So whenever we talk about these equilibrium points in a mechanical system, to be more precise, obviously what is happening is this should be 0, this should be 0, right? Because you would have written your state space in this certain form. Let me just put it here, x1. So let me just x1 equal to y1, x1 dot equal to y1, y1 dot equal to, let's say, f1 of x1, x2. So similarly, x2 dot equal to y2, y2 dot equal to f2 of x1, x2 in this particular case actually. Okay, so obviously when you say vector field is in fact equal to 0, y1 equal to 0, f1 of x1, x2 equal to 0, y2 equal to 0, f2 of x1, x2 is in fact equal to 0. All the vector field quantities on the right hand side, because we have put it back in the same form that we had earlier, right? x1 dot or y1 dot, x2 dot, y2 dot. So this would be y1, f1, y2, f2. so on and so forth. So your vector field, you are just making it equal to 0, and in that particular sense, for your mechanical systems, it would be on the configuration space itself, right? So your equilibrium point would be in the configuration space, right? X1 dot, X2 dot, X3 dot, so on and so forth are already 0. That's the reason I said whenever we do have a pendulum, okay, so let's say that I'm talking about a simple pendulum case here, right? My equilibrium points are somewhere here. So this is theta dot, theta double dot plus sine theta is in fact equal to 0. This is pi, this is 2 pi, this is minus pi, this is minus 2 pi. There are no equilibrium points somewhere here, right? So there can't be an equilibrium point outside of this theta axis correspondingly, because it's a mechanical system that we are talking about. Does it always happen that way, that it should always be on the horizontal axis? Not necessarily. In a general dynamical system that we can think about here, let me just put it as x dot equal to f1 of x comma y dot equal to f2 of x comma y. Okay, f1 of x comma y equal to 0, f2 of x comma y equal to 0 implies some some point which is x star comma y star not equal to 0, maybe, right? Y star may not in fact be equal to 0, or x star may not in fact be equal to 0, where, so I mean, let me just not write that condition actually, because I'm talking about in a more general sense. So both could be non-zero quantities. It need not always be on the horizontal axis. I have seen students thinking that the equilibrium point should always be on the horizontal axis. Okay, that's not obviously the case for a general dynamical system that we are talking about. For a mechanical system, yes, it should be on the horizontal axis or in the configuration space, to be more precise in that particular sense. Okay, so this is a simple case. I think you'd be able to easily derive this equation of motion in this particular case. I remember CP used a bit different problem of this particular kind, where he had a torsional spring at the hub. Okay, but what I have done here is in fact a horizontal spring, and this is a slider, a massless slider. So what I expect that the spring is always in the horizontal position. It will never have any angle with the pendulum. So it can move up and down correspondingly. Okay, I can write a nonlinear equation of motion in this particular form. Maybe we can look at writing this equation later, but I assume that you already know how to do that. Let's convert it into a first order equation form, which is theta prime equal to psi, and psi prime equal to whatever I do have over here. I just take it onto the right hand side. This is the state space form that we are in fact talking about. So in this particular case, I can once again represent it in this particular form, x dot equal to f of x. Okay, x is in fact in R2 for me. I shouldn't have written, this is in angles and angular velocities. To be more precise, I should have said it should be on a circle or something, but let's not, let's not make it that abstract as such. So I will just equate this vector field in fact equal to 0, and I would be able to find out all the equilibrium points. Okay, so once again, in every case, you will see that theta prime is in fact equal to 0. So your equilibrium point is on the horizontal axis every time. Okay, and once again, obviously, depending on the value of beta, this is the non-dimensional form of this equation. Okay, beta is in fact a factor which is which is relating k and the acceleration due to gravity. So that's a parameter that I have got, and one of the set of equilibrium points, which is theta equal to n pi, would exist for all values of beta, immaterial of what is the value of beta. Beta is a real quantity for me, but some of the equilibrium points would exist only for certain range of values of beta, which means beta should in fact be greater than 1 for this equilibrium point to exist. Why? Just because cosine cannot have will be restricted between -1 to +1, and because beta is in fact a positive quantity, what I have is theta could in fact stay somewhere between 0 and pi, let's say. Okay, 0 and pi by 2 to be more precise. Okay, so beta should in fact be greater than unity for this to in fact exist in that particular sense. Now, so that was the equilibrium points for a non-autonomous dynamical, autonomous dynamical system. Okay, can we do something very similar to a non-autonomous dynamical system? Let me just take a minute to in fact look into this particular case. Okay, let me just consider a non-autonomous dynamical system of this particular form, right? Can I just equate it to 0 to find equilibrium points? Can I just equate it to 0 and say, okay, so let me just write it down here once again. X dot equal to minus x plus t is my quantity. So which is, let me just call this as f of x comma t. For equilibrium, let's set f of x comma t is in fact equal to 0, which implies minus x plus t is in fact equal to 0, x equal to t. Happy, fine. So you will say that my equilibrium point is in fact x equal to t, but that doesn't make any sense whatsoever, right? Why? Just because x keeps on changing with time, but you wanted your fixed point to be in fact fixed in time, no evolution whatsoever. If this keeps on changing with time, what really happens is the green curve is what you are getting. With time, when you just plot it, the green curve is what you are getting. But if you just solve this equation, okay, just a very interesting prospect, because it's a first order differential equation, easily you will be able to solve. What you end up getting is as the solution, okay? And just notice that as t tends to infinity, the value of x goes to this particular value t minus 1. Okay, it asymptotically reaches that particular value, which is the red curve over here. Okay, I start with several initial conditions. The blue ones are the initial condition, time evolutions over here. X equal to t happens to be the equilibrium point that we found out. Brute force, we just tried to find out that. But when we talk about the evolution itself, as time evolves, I start with large number of initial conditions. I would see that all of them would in fact converge on to the line which is t minus 1 over here. Okay, you can kindly verify. It's quite easy to in fact check it as well. So what is really happening here, right? We found out an equilibrium position. Even if you start on this equilibrium position, I am evolving. I start with this initial condition somewhere here, I evolve on the equilibrium point itself. Okay, if at all I had started on the equilibrium point, I should have stayed there. I cannot evolve from that particular position. So generally, non-autonomous dynamical systems do not have fixed points. Okay, in this particular case, we do not have fixed points, but it's not a very complete statement as such. Let me just give you another example here. Let's say that I do have a dynamical system of this particular form, right? X dot equal to f of x into g of t. Okay. Now, can I find a equilibrium point for this? Because on the right hand side, I do have a vector field. F of x into g of t is in fact equal to 0. G of t not equal to 0 for all times. Okay, that's not equal to 0. So f of x equal to 0, and I can find a solution x star correspondingly. Okay. Now, if a dynamical system is representable in this particular form, yes, I can in fact find equilibrium points. But if a dynamical system is represented in this particular form, plus g of t or f of x comma t, which is in this form, obviously, I will never be able to find equilibrium points. Okay, just let me just give you an example here, because most of you have studied Hill's equation or Matthew equation, as I hope you know what it is. X double dot plus, let's say, a of t into x is in fact equal to 0. A of t is a of t plus capital T. Okay, so T is finite. Okay, so A of T is in fact, let me just make it a bit more precise. This is in R, which means it's a 1 degree of freedom system. Uh, so what happens is in this particular case, I do have a coefficient which is time variant. Now it's a non-autonomous dynamical system for me. But would it in fact support an equilibrium point? Yes, it does in fact support an equilibrium position, which is in fact x equal to 0, x dot equal to 0. That's an equilibrium position for me, right? So no doubts about it. It is in fact an equilibrium position for me, right? So you cannot in fact say that non-autonomous dynamical system do not have any fixed points, right? Because in this particular case, if you just recollect your study on nonlinear dynamics, the Hill's equation or Matthew equation comes from this particular one of the sources, or let's say one of the systems where this Hill's equation arises is in fact a simple pendulum, right? I think this is a classical example. Simple pendulum being oscillated with a certain excitation here, y of t, right? So this is m, let's say this is gravity, this is L. So this is angle theta, let's say. Okay, so I'm oscillating it in the vertical direction, and that's exactly where you would in fact get a Hill's equation or a Matthew equation. Matthew equation is a more specific form of the Hill's equation correspondingly. Here, if you start with theta equal to 0 position correspondingly, okay, so if you start with the position theta equal to 0, you will never be able to perturb that. So that's an equilibrium position for sure. Theta doesn't change. Is the vertical position changing? Yes, it is changing, but that's not my state variable. Okay, the vertical position of my mass is not a state variable because it's not a generalized coordinate for me. Theta happens to be my generalized coordinate, and theta dot happens to be my generalized velocity. If you start with theta equal to 0, theta dot equal to 0, it would stay there forever. Okay, similarly, let me say theta equal to 0, theta dot equal to 0 is an equilibrium position. Similarly, theta equal to plus or minus pi, theta dot equal to 0 is also an equilibrium position. Okay, so a non-autonomous dynamical system would also have equilibrium positions. Okay, you need to be more clear about how you are representing your dynamical system here. What is the form of your dynamical system? Where is this particular non-autonomous part, or let's say explicit time dependence coming into picture, is something that you need to in fact be aware of. Okay, blindly stating that it doesn't exist doesn't make any sense. That's the reason I say in general, I try to be a bit more precise and give you the other context as well in that particular sense. Okay. Now, coming to the question of stability, I think there are different notions of stability that we can in fact think about. To begin with, we'll talk about stability of equilibrium points. Maybe then we can go to stability of periodic solutions later. Okay, so one of the notions of stability is what is called a Lyapunov stability. Okay, so we start with a very general scenario over here. I will not go through the nitty-gritties or details in this particular sense. Okay, so what is really happening if it is a higher dimensional space, that or a two-dimensional space to be more precise? Let's say that I do have x and x dot. Okay, I do have an equilibrium point over here. So where I have been able to say that that's an equilibrium point. So what it is in fact stating is, so give me a value of epsilon. So let's say this is a epsilon. Okay. So if you give me a value of epsilon, I will be able to find a certain value of delta. Okay. Okay. So a certain value of delta such that if you start inside this particular delta, if you start inside this delta, it would stay inside this epsilon. Okay. It would never go out of that particular epsilon. That's the basic idea. Okay. So I need to be given a certain value of epsilon. I will be able to find a value of delta such that it would never go out of that particular outer circle, which is in fact the epsilon circle. Okay, that's a simple, very simple idea in that particular sense. Now I'm just showing it in the two-dimensional space, but if it is a higher dimensional space, what I end up getting is a ball. Okay, the epsilon would in fact be the radius of that particular sphere. Delta once again would the radius of that particular sphere. If you start within that particular region, you would stay within the region of epsilon. Okay, so let me just make that a bit more clear. Let's say that this is x1, x2, x3, so on and so forth. It's in the state space that I'm talking about here. Okay. Let's say that I do have an equilibrium point somewhere here. So the epsilon circle is in red for me. So it's not a circle anymore. It's in fact a sphere. Okay. So it has a sphere of radius epsilon. Okay. Within that, I will be able to find another smaller sphere of radius delta. Okay. If I start within the delta, I would be able to say that I will stay within that epsilon, right? So that's the basic idea of what is called the Lyapunov stable equilibrium bonds. Okay, so this is quite simple. I think I'm just giving you a overview of what it is, so that we will be able to use some basic ideas later. That's it. Okay, I'm assuming that these are mathematical definitions which you are already aware of. I'm not spending time on that. I'm just giving you a general overview of this particular case. Okay, this is Lyapunov. I think I usually do something a bit different, that I always take a snippet of some of these people who we are talking about. I think we'll see more names and pictures coming out. Just to at least appreciate the kind of work that they have done, we just keep using their work without even acknowledging them. So that's the reason I put up a slide just talking about very basic things about their contribution. Lyapunov stability is what we know of. Lyapunov functions, I think you will be able to see later. I think you might have used it also in this particular sense. Okay. Now, a more restrictive definition is what is called the asymptotic stability. Okay. So it's a more restrictive, let's say, condition, or let's say the notion of stability in that particular sense. So sorry for my movement, actually, if you're seeing my video, because I have a motion sensor in my office. And if I stay in one place, equilibrate at one place, the lights would go off. Sorry, I just need to keep oscillating, actually. So a more restrictive definition, or let's say notion of stability, is what is called the asymptotic stability. Once again, we'll start with the same idea. Just give me a certain epsilon over here, and you start somewhere inside in this particular case. Let's say you give a certain delta over here, right? So delta is what has been provided to us, and I start with an initial condition within this delta. So as time evolves, the evolution, it has to in fact converge on to the equilibrium position itself. Okay, on the same idea, because there is no need of an epsilon circle here. Okay, I have just written it this way, just to show the difference between the asymptotic stability and Lyapunov stability. If this is my equilibrium position, I do have a delta circle, radius delta. I start with certain initial condition close to somewhere here. It would just converge on to the equilibrium position itself, or let's say the equilibrium point. Okay. So that happens to be what is called the asymptotic stability. More often, obviously, whenever we do have a non-conservative system, that is, there is dissipation, you will in fact observe this asymptotically stable equilibrium points. If it is a conservative system, you would end up having a Lyapunov stable equilibrium points only. Either it could be saddles or centers correspondingly, right? In the case of conservative systems, we'll see that a bit later. But in the case of non-conservative systems where there is dissipation, you might come up or end up looking at what are called asymptotically stable equilibrium points. Okay, so that's a basic idea. These are two different notions that we in fact come across and we talk about quite commonly in this particular sense. Let me start with a very simple case. This is a simple damped oscillator. Okay, so depending on the value of K, M, and because all of them are positive quantities, I will not make it too complicated here. All of them are positive quantities as such. So whenever I do have this C is in fact equal to 0, I do have a equilibrium point which is in fact Lyapunov stable. Why do I call it as Lyapunov stable? Because in this particular case, if you see here, this is x and x dot. Okay, so I do have only one equilibrium point. Okay, so if I give a value of a delta and I start with any initial condition here, let me put it here, any initial condition, it would just stay here. It's a periodic oscillation, right? If I change my initial condition, okay, so something like this. Okay, so I think I shouldn't have written this delta here. So that was a mistake. So I should have written my delta much larger. Okay, so the epsilon would be much larger than delta. Okay, I start within this delta radius. I would stay there forever. Okay, it doesn't matter, right? That is in fact what is called the Lyapunov stable equilibrium position. For C is in fact equal to 0. Now, if I just make it positively damped, so the damping is in fact positive, what really happens is, so I think I made a mistake in this particular case. It should have been the decaying solution, right? It would be asymptotically stable. As time evolves, you start from here, it just converges onto your equilibrium position itself. That's a asymptotically stable equilibrium point. Okay. Now, what happens if C is in fact positive? Okay, or C is in fact a negative to be precise. I think the animation in fact got the better of me actually. So when C is in fact negative, what happens is the amplitude keeps on increasing. So it keeps on going outside, right? If whatever might be the epsilon you provide, okay, if I start with certain, certain delta that you are in fact talking about. So I start somewhere here, let's say that, so this is x and x dot. So I start with certain initial condition somewhere here, it just keeps on going out. And whatever might be the epsilon I provide, okay? So if epsilon is somewhere here, it would breach after certain time duration, isn't it? So it would just evolve and it would breach at this particular point. So now you can say I'll make epsilon much larger. Whatever might be the large value of epsilon that you in fact impose, it would just breach at certain time instant later. Okay. So that's the reason we would in fact be an unstable equilibrium point. So just note that this notion of asymptotic stability is in fact the limiting behavior, not for finite time durations. So t tending to infinity is what we are talking about. You will see that asymptotically it would in fact converge on to that particular point. Converge on to the equilibrium point. But once again, note that it will never be able to reach the equilibrium point itself. If it reaches the equilibrium point, you would have loss of information, loss of determinism, whatever we spoke about earlier. Okay, so that's the reason as time tends to infinity, it would in fact reach the equilibrium position point, and you will never reach that equilibrium point forever. Okay, so that's the basic idea. Now, the linearization is something that you already have done. I think CP spoke about the Jacobian matrix and so on and so forth. I'll not once again speak about all these things because you're already aware of these things. We start with a certain equilibrium position, x star. When I say x star, just be sure that when I say x star, it is in fact x1 star, x2 star, x3 star, xn star. Okay. That is in fact a point in your n-dimensional state space. Okay, it's not a single point, it's not a scalar value, it's an n tuple, and you will be able to say that in that n-dimensional state space, it's a point that I'm in fact talking about. Okay, there are n of these values. Obviously, you are aware of that. When I do perturbation of that particular n tuple, obviously what I would once again mean is x1 star, x2 star, xn star plus y1 of t, y2 of t, yn of t. Okay, so in each of these state space, or let's say state directions, or let's say states, I would be adding a small perturbation to that particular direction correspondingly, because I'm talking about, or not direction, to be more precise, the coordinate itself. Okay, so I'm just adding a certain perturbation to that particular point. So I do end up getting a linearized equation. Okay. Why do I call it linearized? Because in this particular case, I do have y dot equal to A, which is in fact a square matrix, into y, which is in fact once again a vector. Here it is in fact a state vector, which is in fact a perturbed state vector. Okay. And a Jacobian is defined in this particular form. I think you are already aware of several such matrices. I think you maybe a digression. This is what is called a Jacobian matrix. You might have heard of something called a Hessian matrix, right? Maybe just look back at what that Hessian matrix is all about. Okay, there is something else called the Wronskian matrix. Okay, just throwing up some terms so that you can just look back, some interesting facts about functions theory also. There's something called a Wronskian also. Okay, so Jacobian in this particular case is just a transformation between these two different coordinates basically. So this matrix A is what we would be interested in as we proceed further. Okay, now I do have a autonomous dynamical system. As I said, we'll not bother about non-autonomous dynamical system because problem becomes a bit more tricky over there. Equilibrium points may not exist, so on and so forth. So I consider an autonomous dynamical system, and its linear version is over here. Okay. Now, if this coefficient matrix is non-singular, okay, so if the coefficient matrix is non-singular, then the the system is in fact called a simple system. Okay, a linear system y dot equal to ay is said to be simple if the coefficient matrix A is non-singular. Okay, obviously this would happen only if some of the eigenvalues of your matrix A is I mean, if it would become singular if some of the eigenvalues of your matrix A is in fact equal to 0. Okay, so that is something we will in fact talk about now over here. So this would in fact be a simple system where the determinant is not in fact equal to 0. Okay, so when do we call an equilibrium point to be hyperbolic? When all the eigenvalues have non-zero real parts. Okay, so your eigenvalues of your particular matrix is in fact particular Jacobian matrix happens to be something that defines the linearized stability. Okay, so we would be interested in knowing the eigenvalues of this particular matrix if all the eigenvalues have non-zero real parts. Okay, the non-zero real parts is quite important. It can have imaginary parts, it may not have imaginary part, doesn't really matter to us at all. In a very general sense of stability analysis, it doesn't really matter if it has imaginary parts or not. What we would be always interested in is the real part of the solution. If every eigenvalue in this particular case has non-zero real parts, then such an equilibrium point is what is called a hyperbolic equilibrium point. Okay. And whenever even one of the eigenvalues has a zero real part, then we call it as a non-hyperbolic equilibrium point. Okay. The study of hyperbolic equilibrium point and its analysis is quite simple. Okay, no big issue. I don't think if every equilibrium point were in fact hyperbolic equilibrium points, I think nonlinear dynamics wouldn't have evolved in this particular format. Because when we talk about bifurcation theory, once again, the equilibrium point loses its hyperbolicity, or let's say the real part in fact passes through zero. That's exactly where the bifurcation happens. The bifurcation theory wouldn't have existed, or center manifold theory wouldn't have existed. Center manifold reduction may not have in fact happened as such. Okay, so the loss of hyperbolicity leads to a very different kinds of dynamics, and that's exactly what we would in fact talk about. That's the reason I'm just giving you so much of background. Maybe it is overdone, I don't know, but let's see how it proceeds further. Okay, so now so why do we in fact are interested in the linearized systems? Okay, so because we started off with the idea of a nonlinear system, now we came back to a linearized version. Okay, so let's consider a nonlinear autonomous dynamical system x dot equal to f of x has a simple equilibrium point, which means the matrix A, the Jacobian matrix A, is non-singular. Then, in the near neighborhood of the equilibrium point, the phase portraits of the system and its linearization are qualitatively equivalent. Okay, qualitatively equivalent, provided that the considered equilibrium point is hyperbolic. I think this is a overstatement to be precise, because I have already mentioned that there is a simple equilibrium point. Okay, but still, let me make it as precise as possible over here. We are just saying that whenever you do have a hyperbolic equilibrium point, and we are looking at the near neighborhood of that particular equilibrium point, its phase portrait would in fact be same. The linearized phase portrait and the nonlinear phase portrait would in fact be qualitatively equivalent, not quantitatively. It's not one-to-one correspondence that you can in fact, or let's say magnitude wise similar, but we are talking about qualitative equivalence, right? So we will see that particular cases later also when I show the linearized eigenspaces and the corresponding nonlinear evolution also. You would see, you would agree with me with this particular notion that for an hyperbolic equilibrium point, near that particular equilibrium point, you would have these phase portraits to be in fact similar, qualitatively similar. Okay, so let me not just go through this particular statement here. This is quite self-explanatory. Maybe if the slides are shared with you, you can just go through that. This is a theorem that you need to be aware of. Okay, so don't just ever say that just because I'm doing linearization, it would always be same. I'll show some cases where it will not happen so. Okay, because you will in fact see that if it is not a hyperbolic equilibrium point, it can show a very different picture also. Okay, so if you just look at these two dynamical systems, they are equivalent because both of them would in fact give somewhat similar solutions, or let's say they both are in fact asymptotically stable equilibrium points. As I remember, I didn't work it out, just work it out actually. And you will be able to say that these two are in fact equivalent, qualitatively equivalent in that particular sense. Okay, just be aware of all these conditions that I'm in fact posing. They're not for making things abstract, but rather they are extremely relevant to the statements that I have in fact made. Okay, so none of the statements made here are just for filling up spaces actually. So with some intention, with just not to make things ambiguous, I'm just trying to put things together in this form. Okay, now, so why do we study linear system? Obviously, once we have a linear system and A is in fact non-singular, okay, so that's exactly what we have in fact found out, and you would be able to find the corresponding eigenvalues and the eigenvectors. As simple as that. So we start with a certain ansatz, or let's say a certain assumed solution, e power lambda t into v. So whenever I say e power lambda, so let's say this is y of t is e power lambda t into v1, v2. So even on the left hand side, if I just have to make it more precise, I may just have to put it as y1 of t, y2 of t equal to e power lambda t v1, v2. So v1, v2 do not have any argument because they are constant values. Okay, because this is a linear system that we are talking about over here. v1 and v2 are in fact constant values. You would be able to find the eigenvalues. As simple as that. Okay, so there are two eigenvalues and correspondingly two eigenvectors. So what's so special about that? So the speciality of these linear analysis happens to be that any configuration, or let's say any state of the system, would in fact be a linear combination of these two states. Okay, that's the reason I think CP did talk about this basis functions. Okay, so the basis happens to be the bedrock of linear analysis actually, right? So because you have these basis vectors, and any state is in fact a linear combination of these. Okay, you can't have just one of them. You need to have both these eigenvectors and eigen values corresponding. It can't be just one. Okay, so any state would in fact be linear combination. So that's once again a theory, or let's say theorem. I think if you go through a very standard book on dynamical systems or differential equations, you would in fact be able to go through these basic theorems actually. I'm not going through the proof of all of them. Even if you go through a book on linear algebra, you would be able to understand why we in fact talk about all this actually. Okay. Now, as I said, I'm just doing a summation of all of them, right? This you can in fact put it as a vector. As I said, I had used these slides for a different course, in fact, where the assumptions were previously made that these are vectors. A priori, I had mentioned that. So this is the reason I put it here. Y in Rn, which already means it's a vector. Okay. So I don't put this curly brackets. Some places I explicitly do that also, just to clarify. And some of these lecture notes from, as I said, from different courses might be a bit confusing, but this is exactly what it is. Okay, a linear combination of these two. Now, when you talk about this particular case, there is a positive value of lambda and there is a negative value of lambda. The positive value of lambda corresponds to what is called an unstable manifold. Why do I call it unstable? Along this particular direction, any trajectory, if I start any initial condition somewhere here along this direction, obviously it would go to infinity. It would go away from the equilibrium point. Okay, so that's the reason I call it as an unstable manifold, or let's say an unstable eigenspace. So this is what is called a linear eigenspace, right? So this is usually what is called a linear eigenspace. When we talk about center manifold theory, I'll clarify it once again over here. This is called the unstable manifold, or let's say the unstable eigenspace correspondingly. Similarly, I would have another eigenvalue, which is in fact negative. Lambda is negative over here. This is what is called the stable manifold, or let's say the stable eigenspace correspondingly. Now, in that particular sense, because here we do have only two eigenvalues, okay? So one of them is stable, the other is unstable. Let's say I do have an n-dimensional space, okay? Let me just put it here, n dimensional space, okay, with let's say k eigenvalues with real part of lambda less than 0 and L eigenvalues with real part of lambda greater than 0 and KLM, let's say, eigenvalues with real part of lambda equal to 0 and K plus L plus M equal to N for me. Okay, simple. because it's an n-dimensional space, I do have n of these eigenvalues, of which k eigenvalues, and I'm talking about and equilibrium point, and x equal to x star is the equilibrium point at which I'm trying to find out the eigenvalues correspondingly of the linearized equation of motion, or let's say linearized equation correspondingly. So this is how I'm writing it here. One second, sorry. Y dot equal to a y, and this is n cross n, and obviously it has n eigenvalues, k plus l plus m. Okay, this set of eigenvalues are what are called the stable eigenspaces. Okay, stable eigenspace for x star correspondingly. Okay, es, so that's the e for eigenspace, s for the stable eigenspace, because real part of your lambda is in fact less than 0, so I call it as the stable eigenspaces. Okay, similarly unstable eigenspaces, once again, okay, for L of these eigenvalues and corresponding eigenvectors, to be more precise, okay, that would correspond to a space which is EU. U corresponds to the unstable eigenspace, okay, and there is something called the center eigenspace, because you do have real part is in fact equal to 0, that corresponds to eigenvectors which have corresponding eigenvalues have 0 real parts. Centers doesn't necessarily mean you do have periodic oscillations. In the parallels of nonlinear oscillations, nonlinear dynamics, or dynamical systems, centers do not necessarily mean that you do have periodic oscillations around that equilibrium point. No, it's not the case. It just says the eigenvalue has 0 real part. Immaterial of having a imaginary part or not, it doesn't really matter, but it just says the real part of the eigenvalue is in fact equal to 0. Okay, so that's the basic premise. I think we will come back to this particular part later. I'll use a bit different notation, but ES, EU, and EX, let me just put it once again here. ES of X star has k vectors. Okay, EU of X star has L vectors. Okay, EC of X star has, okay, so if I say that I do have 0 eigenvalue, or real part is in fact equal to 0, then what do I mean by eigenvectors there correspondingly? Okay, I'll not write anything. Let's go back to that particular point bit later. So would it still have these m vectors correspondingly? These two are quite clear, right? So real part is in fact equal to not in fact equal to 0. One is positive, one is negative, so it is clear. But what happens whenever you do have the real part is in fact equal to 0? That's something that we would come back later. Okay. Maybe I think we will take a break right now. It's 11:30. I believe it breaks at 11:30, right? So
Yes.
we'll catch up in another 15 minutes, right?
Yeah, sure. Yeah.
Okay, thank you.